Okay, good afternoon. Yeah, I think everything is switched on. First, I would like to thank the organizers for putting together this very interesting activity, and personally for inviting me to this lovely institute and to this beautiful city, and thank you all for coming here after lunch. So my name is Baruch Meerson. I'm from the Hebrew University of Jerusalem, and I'll talk today about a specific problem which I think, well, it's supposed to be important in condensed matter physics and in the other areas, but it also illustrates some general recipe, actually two different general recipes of working with a broad class of problems. So I hope to elaborate as I go. And this paper was published like half a year ago. So this is an outline. I'll probably not take the whole hour. Essentially, the work is about the motion of a particle in a disordered medium at low temperature. And there are many local minima, and the temperature is very small, so the particle most of the time doesn't do anything, but then there is an activated escape to another potential well, and then it continues from there. So this is more or less the framework. So we'll see that the key quantity to be able to compute in this problem is to compute is this distribution of the potential barriers. So if there is a random potential, and the potential barrier is essentially the difference between the maximum and the adjacent and one of the adjacent minima. So how this quantity is distributed, and what is more relevant here in the limit of the temperature going to zero, how does the tail of this distribution look like? The tail of large delta V, of large potential differences. So, and then, because this is a large deviation workshop, a large deviation activity, it's not surprising that we will see a large deviation here and some optimal configuration, a most likely configuration of the potential which satisfies the imposed constraints. And then I'll be talking about the role of autocorrelations, or more specifically of negative autocorrelations. Some of these things were known for quite some time, but the role of negative autocorrelations, if the disorder has some negative correlations in it, autocorrelations, was apparently missed. And if time permits, which I think will happen because it's not a long talk, I'll also mention, like as an advertisement, a couple of other problems which are already not related to particle motion at low temperature, but mathematically they are other additional instances of how to deal with large deviations, of certain kinds of large deviations of non-Markovian processes, which are Gaussian. Okay, so this is more or less the plan. So the paradigm of overdamped particle motion in a static disorder potential, it is called quenched disorder potential, when there is thermal noise, but the temperature is small, is an important paradigm in many applications. And here I list some of them. They look very different. While transport of electrons, holes, and excitons in disordered metals or semiconductors, it's where it comes to the condensed matter physics, but also the viscous flow of supercooled liquids and glassy matrices, essentially glasses, is also a nice illustration of the same concept when you have many local minima in the system, sort of slowly crowning from one configuration to another. And even in the live molecule, the DNA macromolecules, there is a similar scenario and even similar math. But recently, like in the last more or less 10 years, there are now colloidal systems in quenched random potentials created by laser light. So it's a controlled potential. It can be deterministic, it can be disordered, And you can study, using the confocal microscopy, you can study the motion of particles, thermally activated motion of particles in a controlled way, in a potential which is sort of disordered by control. It's created by laser. It's become experimentally available, so some of the things hopefully can be tested in experiment. Okay, so this is the basic model, and it will be 1D. So essentially we have a one-dimensional over-damped motion of a particle. X is the particle coordinate. And there are two sort of reasons for its under-damped motion. One of them is essentially the force that comes from a quenched potential. V of x is an external potential. It doesn't depend on time. And the other term, the noise term, well, actually the first one will also be a noise term, but this is a sort of a time-dependent noise term. It's standard noise term, which describes the thermal noise. So D is the bare diffusion coefficient, which is essentially proportional to the temperature of the medium. When D goes to zero, I'll be talking about, this is the case I will be talking about, is when the temperature is small. So V of x is given, but it's a given realization of a disordered potential. So it's essentially a random function of x. So I will have to assume some statistical properties of this function before I can do any reasonable calculation. Okay, so the rest I explained. So this is a sort of a image of realization of the potential, and please disregard these stupid things. This is some sort of artist's fantasy, and I was lazy not to sort of didn't produce my own picture. So there are not, I mean, the probability to see a flat configuration like this is small, so don't take it seriously. Okay, actually there's a very long list of papers. This is a very small sub-list out of that list, probably the most prominent papers. Well, let me put it more accurately. This is the papers that were most useful for my purposes, which essentially deals with this paradigm, with this basic model. So it started with the work of Dejean, and then there was work of Basler in the context of glasses, and that's Zwanzig did more mathematically oriented work without knowing anything about Dejean and Basler. And then Lopatin and Vinokur published a paper which is very close in spirit to what I'm doing in this paper. Essentially, I'm following their footstep. And Lopatin and Vinokur didn't know anything about any of these three. And then the later papers already knew everything about Dejean and Basler and Zwanzig, but nobody knew about Lopatin and Vinokur, despite the fact that it's a fissure of letters. So science is developing, you see, not in a monotonic way, not in a logical way. So some people rediscover other things, and so. But all these papers are important, and there are many more, actually. There are many more. Okay. So what is the picture? As I already hinted, a particle quickly settles down in a local minimum, and then it takes, an unusually large fluctuation activated by noise, by thermal noise, to overcome this barrier, and then again it settles rapidly towards this minimum, and then it can go here, and then it goes here, and then sometimes it can come back, and so on and so forth. So when the potential is given, so this is just, a very complicated and not very interesting problem of activated escape in a specific noisy realization. So what would be more interesting to do is to somehow predict the statistical properties. So this picture of a local escape over a given barrier is essentially the Kramer's picture. It is a classical stochastic physics. It's well known, but it relates to the given potential V of x and the given delta V for that matter. Okay, so and this result is already a result of somehow averaging over the noise, right, over the thermal noise. But what we essentially want to do in this paper is to additionally average this escape time over all realizations of the potential, assuming some given statistics of this potential, this disorder potential. Okay, please interrupt me as I speak, but in this case you will have to grab the microphone because we are being recorded. Okay, so as I said, to determine the mean escamber, the additional averaging is performed over the disordered potential. So we make an assumption that we check a posteriori that this potential, okay, just a moment, no. As I said, we need to suppose some properties of the potential. So what we will assume, or what rather I assumed in this paper, is that the potential is statistically stationary. So if x is time, so that's a stationary process. But v of x is just a stationary function, and it is that its statistical properties are independent of the location, right? So this is what we assume. And also, we assume that v of x is normally distributed. Okay, so it's a Gaussian process with some zero mean and with some given variance. And a bit later, I will prescribe an autocorrelation function, autocovariance, how you call it in different areas. It is called differently, which would completely characterize the properties of this Gaussian process. Okay, so we are essentially we need, if we go back for a moment to the Kramer's formula. And I will not be interested in the pre-exponential factors. All this, what I will be talking about here, is with accuracy up to pre-exponential factors. So I'm only trying to capture the exponential dependencies. Well, it depends. It will definitely be not important in this paper, in my talk and in this paper, because essentially I assume, I mean, a good question is, when is it important and when can it be ignored to the first approximation? It cannot be ignored if this temperature, which is bare diffusion coefficient is large. Then essentially what you have in the exponential delta V over D is of order 1, and in this sense it has no meaning to talk about exponential dependence as a leading order dependence. But when D goes to 0, okay, I assume that this exponential dependence is more important than the prefactor. So if instead I'll take the logarithm of T, so the exponential will give me just delta V over D, a linear term in delta V, while the pre-exponential factor will give me a logarithmic correction in this representation. So in this talk, I will be essentially ignoring these logarithmic corrections. Oh, just a moment, we are breaking the rules. Yes, please, yeah. Try to switch it on, maybe it is switched off. Oops. There is one button there. Oh, now it is on, thank you.
Do you assume that the distribution of the V is temperature independent?
The distribution of delta V is definitely temperature independent. It's a static potential. It comes from disorder. It doesn't come from the temperature. I can take, you know, some dirt and it will be disordered, or some rock. It has nothing to do with the temperature. And then I can heat it to a high temperature or cool it to a low temperature, but the disorder, you know, the structure of the medium will remain the same. Mm-hmm. So the temperature, the fluctuations coming from the temperature and fluctuations coming from the disorder of the potential, they have completely different origins, and yeah. So.
And another question is there, as you go to low temperature, do you consider possibility of tunneling also?
No, it's a very good question, because there is also, of course, a competing process of tunneling, and then people worked on this in the context of purely Kramer's problem. What would Kramer's problem look like if there is also quantum effect? There is, well, I forgot the name. There is a very good APRL about it, an American scientist, well-known one, but I forgot the name. It will come, probably it will come back. Yeah. No, it's a correlated process. It's a correlated process, and this is the name of the game here. So, and this is the reason that it is not Markovian. Yes, I will be interested in mean escape time when this Kramer's time averaged over the disorder. Oh, yes. That's of course. I don't know how to compute it. Well, the complete distribution is in a halt, I would expect that the complete distribution is sufficiently complicated and interesting. For example, to such an extent that the average and let's say median will be very different. So it's a non-trivial distribution. So in this sense, that I will compute the average t is just my decision. It's one of the quantities that can be computed. Doesn't mean that it is sort of a good representation of the whole distribution. That's an excellent question, yes. Say it again, please.
This average t, in principle, can be written down for any realization of the potential, right? There's an exact formula for the average mean for spaces time given a potential.
Oh, yes, when the potential is given. Exactly.
Given, so
exactly.
Then you have an exact expression for the average mean for spaces time.
Yes, you can do it. You can do it under some assumption of the delta correlated noise and so on and so on.
Yeah, if the noise is delta correlated, but noise is the thermal noise is delta correlated.
The thermal noise is delta correlated.
Yeah. So then you can write down for any potential given that it in infinity it's sufficiently confining or something.
Yes and no. Because in this exact formula, I mean, you prescribe V of x, essentially what enters the result in the limit of d going to 0 is essentially the minimum value of the potential.
I didn't mean the Kramer's calculation, but you can write down a differential equation for the average t and you can solve it for any given potential. Right, Seta?
Yeah. Yes, there is an exact formula, quite a complicated one. I cannot imagine how you can average it over the distribution of V of x, even if the distribution of V of x is known.
It more or less looks like the formula you have written down, but it's like a double integral, basically.
Yes. Yes, but how do you define when I'm talking about escape, I'm talking about a specific minimum, a specific maximum, right? So they must. Oh, exactly. So then you need to average not only over all potentials, but over all possible positions. I don't know how to do it. Okay. Okay, let me continue. Did I answer the questions? Okay. So this is what I assume, that it's a stationary, statistically stationary, normally distributed potential. And what we will, of course, want to find in some sense is the distribution of the potential barriers. Because in the Kramer's formula, if I take it for its face value, I need to average it over all delta V, right? This is easily said and done because we don't have the exact result for the complete, not only we don't have the exact result for the complete distribution of delta V, but this complete distribution would be meaningless actually. It would be an excess of accuracy because the Kramer's formula, as I used it, already assumed that delta V is very large. So delta V divided by D is a large number, okay? Otherwise, I couldn't have ignored the exponential factors and so on and so forth. So in some sense, if we want to remain within the Kramer's logics, okay, so that this is activated escape and not just a motion under noise, I essentially am interested in the tail of this P of delta V, and the tail of delta V going to infinity. So this is what I'm trying to find here. The tail of the barrier height distribution corresponding to very large barriers. So let's assume, and we will see that this is indeed what happens. At large delta V, a convenient representation for this tail is like this. I mean, I'm even not assuming that it is exponential, but I assume that sort of that S of delta V is some reasonable function, which will be essentially a simple power law. So I assume this form where S of delta V is a priori unknown. So let's assume that this is so. Then the average over the realizations of the potential is a quantity like this. Okay, so here is the Kramer's mean escape time, and here is what comes from the barrier distribution. So now you see when d goes to 0, you can evaluate this integral by the Laplace's method or by the saddle point, depending on the jargon that you are used to. And then you can evaluate this integral just as exponential at the saddle point, okay? And this saddle point, it comes from the condition that the derivative of this function inside the exponential with respect to delta V is equal to 0. So this is the equation, okay? So, which means that the moment that we find this saddle point delta Vs from this equation, so if we know S of delta V, then we can find S of delta Vs, we can plug it here, and we get the exponent, the average over the realizations, okay? So this is the logic. So now my purpose is to find this function. Okay, so now we assume that V of x is what is called a short-correlated process. Short-correlated essentially means in this context that if I define the covariance, the autocovariance or autocorrelation function, this is a stationary process, so this autocovariance depends only on the difference between x and x prime. So I can always write it down as some constant times the function kappa of x of minus x prime, where kappa is normalized to unity. This is just a convenient definition, okay? So essentially when I say short correlated, I assume that this integral of this type is finite, so that it converges, which means that the correlations cannot be power law with a sufficiently small power exponent. Otherwise, this integral will diverge instead, and the technique changes, and I'm not even sure that I have something smart to say of how to do it in that case. But here we assume that this sort of total spectral density of the process is finite, and this is of course an even function. And when we have this kappa of z, sort of like a normalized autocovariance function, we can define the inverse kernel. And the definition is like this. So you integrate this k, capital K, times this kappa, and when you integrate it over x prime prime, you get a delta function. So to give you some motivation where it comes from, just think about a discrete version of this process. Instead of a continuous v of x, we can consider, a discrete process. Then instead of the autocovariance function, we would have an autocovariance matrix, okay? It would be just a matrix which describes you the correlation between different points in space. And this guy would be the inverse matrix. And here, instead of the delta function, it will be a Kronecker delta. Okay, it's just the inverse matrix. Okay, but if it helps you, if not, it just let's take it as a given. So assume that we solved this integral equation for a given kappa. Okay, the kappa is given, and found this inverse kernel. What can we do with it next? What is it good for? It is actually tremendously important. Yes, please.
I don't know. So if it is exponential, then what is the inverse function? Do you know? If small case exponential tail?
It's not trivial, For every function, you have to solve this equation and to find.
So it's not a trivial function
It's not trivial. To find this guy explicitly, In most cases, it's a very hard task. More than that.
If you have a delta function, I guess the other one is also delta function. No.
No, not at all. This object is also very singular, actually.
Okay.
Okay. Yes, yes, yes.
Okay, okay. Yeah.
Yes, but more often than not, if you try to bring it back to the real space, it is both technically difficult and very often it doesn't exist at all because this is a highly integral object, a highly singular object, more often than not. Okay, so, but we will see that there is a little miracle here, and I will not need the explicit form of K. And this is an important sort of take-home message for many problems like this, relatively simple problems like this. Okay, so if we know this K, as it is written here, the knowledge of K enables us to write down the statistical weight of a given realization of this short-correlated random field. So, and we can write it down as an exponential of minus capital S, where capital S, essentially the action, it looks like this. So it is non-local, so this is the action. Which gives you the probability to observe a given realization of V of X up to a per-exponential factor. And how does it look like? First of all, it is non-local. You see, there is X and there is X dot, and their connection is through the inverse kernel of the covariance. Well, otherwise, it's just a double integral. So this describes, this quantity essentially is the action of a given realization of this noisy, of disordered potential. Okay, so the key observation here is that because we're interested in the tail of the barrier distribution, of the barrier, of the height barrier distributions, which corresponds to very large delta V, this tail is dominated by a certain unusual, I mean rare, but most likely configuration of the potential, which is conditioned on this delta V. So we look at a different realization of the potential, and we say, what is the most likely shape of this potential V of X if we condition it on having at some point a very large given specified delta V. So this is the optimization problem that we want to solve. And it's actually the first paper that known to me that used this logic. They computed a bit different thing, but this is almost equivalent to what I've been doing here was this paper of Lopatin and Vinokur. Optimal configuration of the potential conditioned on some certain property of it. So, and the formalism to use is what we call OFM, optimal fluctuation method. It appears in many different branches of theoretical physics and also mathematical physics. In the mathematical physics, it is called weak noise theory, and in math simply, it is called the instanton theory in condensed matter. It is called optimal fluctuation method. It is called macroscopic fluctuation theory if we are talking specifically about large deviations of lattice gases. But this is more or less the same or closely related family of formalisms, which essentially all of them can be viewed as a WKB approximation for dissipative systems. Traditionally, WKB approximation appeared in the context of waves and then quantum waves, quantum mechanics. But its analog exists in dissipative systems. This is what essentially Freidin and Wenzel were the first to show in the math literature. And so this is one of the members of this family. So now the problem to optimize. So let's just put some local maximum at x equal L and local minimum at x equal minus L. So we subtract these from that, and we essentially condition the process on a given value delta V it can be taken positive because of the symmetry. So the left one is a minimum, the right one is a maximum, which is written here. Here I assume essentially that the optimal configuration that we haven't found yet, it is smooth, so it has these two derivatives, the first and the second. It turns out that this assumption can be relaxed. And of course, there must be no other extrema on the interval between minus L and L. And in addition, I need to minimize the resulting action over all possible values of L, because I don't know the distribution of the distances between the minimum and the maximum. There is some distribution, which I do not necessarily know. So if I were solving the problem exactly, I would have to compute the distribution of delta V for a given L, and then integrate it over the L distribution. But again, it would be probably even in excess of accuracy, because I'm looking at the tail of delta V going to infinity. I have this small parameter d going to 0. So essentially, instead of looking for the whole distribution of L, of the distances between the peaks, the peak and anti-peak, I essentially must look for the optimal value of this L, which gives the largest, the dominant contribution to the action that I'm after. Okay, so now I just minimize this function now, and it is convenient to introduce, essentially to introduce this constraint in terms of a Lagrange multiplier. And because it's a local constraint, there are no integrals here, what I can do, I can put here delta functions at x minus L and x minus, and oops, it must be a plus here. Here there must be a plus, sorry. So these are the two, the peak and an anti-peak, and this guy essentially describes their difference. So I just plug it inside the action, and I need just to minimize this guy with respect to V of x, subject to the conditions that I listed before. So the linear variation must vanish. And in this case, you know, the action is non-local. For a local action, just a moment, for a local action, thank you. For a local action, I would get the Euler-Lagrange equation as we get in classical mechanics. But here, the action to minimize is non-local. So as a result, the analog of Euler-Lagrange equation is an integral equation. Please, Satya. No, I don't put them in hand, but then I study the solution obtained without these demands and just inspect whether these solutions satisfy or not the other conditions. Okay, it is more practical, and you know, and it works. Prefactor? No, forget about prefactors. No, Of course, exactly. Yeah, now I understand the question. The question was, essentially was a comment or conjecture that whether it is smooth or not is not important if we are only looking for the exponential, for the leading order effects, and ignore the prefactors. Did I understand you correctly? Yes, and I completely agree. Okay, so the linear variation must vanish, and we get this equation. It's essentially a linear integral equation for this function V of x, which is, of course, now completely deterministic. It's a most likely configuration. There is no noise here anymore. And you think that you're stuck because you don't know this inverse kernel. But actually, you don't need to know it, because you just compare this equation with this one, and you see there's a bunch of delta functions here, and you immediately guess the solution. The solution is just directly related to the form of the covariance. You see how beautiful it is? So the optimal configuration of the potential is just the difference of the same autocovariance function, and the k is gone because of these conditions. So this is the little small miracle I told you about. You can guess the solution or actually even obtain the solution. You can integrate the both parts, multiply it by kappa, and integrate it, and then you just get it without any guessing. But of course, it's easier to guess. Okay, but it's not the final result yet, and the reasons are two. First, there is this L dependence, and we must optimize with respect to L. And the second is that there is this lambda, this Lagrange multiplier that we need to express through a given quantity, which is delta V. So the second one is very simple, but the first one is a bit tricky. So because V of x is an odd function of x, so let's just demand that at x equals L, we have a maximum. So I just differentiate this guy with respect to x, and of course I drop lambda, and I have this condition that has to be satisfied. Okay, so this is the condition that's sort of a necessary condition for it to be x equal L, to be a maximum point of the potential. So now, if this covariance is smooth, and of course we know that this is an even function, then the first term vanishes identically, and we have this condition. So the second term must be equal to 0. And now everything depends on whether kappa as a function of x is monotone decreasing or not, or oscillating. Let's start with a simple case. With kappa of x is a monotone decreasing. It's a function like that. And of course, you know, symmetric at negative x. In this case, of course, the only way to satisfy the condition that this guy is 0 is just to move L to infinity. So, and we arrive at a solution. It's actually a family of solutions, but they are, again, the same at the level of the exponential dependence, if we are not interested in the pre-exponential. And essentially, the optimal configuration of x, very counterintuitively, consists of two independent pulses, so let's say a spike and an anti-spike of the potential, and each of them essentially reproduces the form, the shape of the correlation function itself. Okay, so this is the most sort of probable, the most likely configuration of the potential conditioned on a given delta V, when this delta V is very large. Yes, I'm escaping from here to here. And of course, this part comes for free if you're not interested in the pre-exponential. You just move ballistically and pay 0 action for that. Okay, so now we go further. So now we can calculate, so we are still in the regime where kappa is monotone decreasing. And of course, it means that there are no negative correlations in the system, because the kappa must go to 0 at infinity, otherwise the integral would diverge. So if it is monotone decreasing, it just boringly goes to 0, and then we have this solution. And in this case, you can compute the action. Again, you don't need to know k for that, because you just identify the combinations of k times kappa, because you know V includes this kappa dependence, and as a result, you use essentially the same orthogonality definition, a connection between k and kappa, and you compute, and you get quite a simple, even boring Gaussian distribution. You see this quadratic action with respect to delta V. When you plug it in the exponential, you essentially get a Gaussian distribution, a Gaussian tail of the distribution of delta V. And what is important, except that it is Gaussian, it is independent of the shape of kappa. What matters here is only the value of the variance. C at 0, it's A times kappa of 0. It's just the variance of this process. So as a result, you go back to this saddle point, Laplace's formula for the average over the realizations of the potential, or average time to escape, and you get this very beautiful result, which coincides with that obtained by Dejean and by Zwanzig, and they use completely different methods. I mean, this method is completely different from this, and both of them are completely different from this. So you just reproduce this result, and notice this result. It's a very, very beautiful result. in comparison to the, it's an old result, again, it's not mine. In contrast to the Kramer's formula, it has 1 over square root of 1 over squared of temperature dependence rather than 1 over d. It's 1 over d squared. So when d goes to 0, this time is huge, okay? So it's a very strong, how to say it, suppression of activated escape. And why is it so? Because if there is a distribution of potential barriers, among them there are some huge ones, and it is there where the particle is stuck. And you work it out and you get this result. The mic. Thank you. Please, Martin. No.
So just a question related to that point. So therefore, don't you want to calculate the average of the typical t? So the average of log t or something like that?
I would like to, but I don't know how.
Yeah.
So, yes, I would like to know much more about this distribution, to evaluate some different averages, to evaluate momenta, but it's you know, it's the first work. Well, I'm still talking about, well, maybe the calculation is new, but the result is classic. So now I'll be talking about something more interesting. And this is the case when kappa is non-monotonic. Okay, you can have. Actually, there are 2 sub-cases here of non-monotonic correlations. You can non-monotonic but boring, you know, function where there are no negative correlations. So the kappa goes to 0 non-monotonically, but never crosses 0. This is the first case. And the second case, more interesting, that it crosses 0. So there are correlations, positive correlation, then there are negative correlations, and then somehow it approaches 0, or either from the negative part of them or positive part. Okay, so these are two sub-cases. But let's first just consider a formal solution. Now we can, this term drops to 0 because of the symmetry and smoothness. Now we can satisfy this condition that this guy is 0, not necessarily at L equals infinity. L equals infinity is still a solution, okay? But now there can be another solution. If x equal small l is the minimum point of kappa of x closest to x equals 0, I can consider, for example, another solution where capital L is just this small l divided by 2. Now this guy is 0 at a finite distance. So let's just evaluate this new solution. First of all, it looks like this. Now these 2 guys are coupled. They're not far from each other. And then you compute the action, and you get a little bit more interesting result. This result is still Gaussian, so it's quadratic with respect to delta V, but there is this a difference of kappa of 0 and kappa of L. And I can put this A inside and get essentially C, capital C of 0 minus capital C of L, which means now that the explicit form of the correlation function becomes important, or more precisely, where is the minimum, the local minimum of the correlation function. And then you go back to the saddle point calculation of the average time, you get this result. It's still an exponential result. It's still exponential with respect to 1 over d squared, exponentially large. But now it depends on the covariance. And now the question, which of these solutions is correct? Because obviously the solution where this guy vanishes because capital L is infinity is still a solution. Which of them is correct? First of all, how do we know which of the solution is correct? The name of the game here is the minimization of the action. If I have more than one sort of candidates, more than one critical point or critical solutions, I have to compute the actions on each of them, and I have to pick up the solution with the least action, and I have to mercilessly sort of discard the other solution. But there is a little bit more to it. Let me show you. So first of all, how this solution, how does it look like? Now I need to consider two separate cases when the negative correlations are present and when they are absent. When they are present, so the correlation function can look something like this, for example, and then the optimal configuration of the potential looks a bit more interesting than before. And here, because C of 0 is negative, C of L is negative, we see that this number, this numerator is larger, let's say by a factor of, I don't know, by 50%, by 30%. It is larger than in the previous case. But because we divide here by d squared, this factor describes actually a giant increase in the mean time to escape, simply because it's exponentially large with respect to a finite number divided by d squared. Okay? And in the other case, the correlation function is non-monotonic, but there are no negative correlations. In this case, actually the solution for which L equals infinity, it wins because it has the least action. So this kind of solution will be incorrect in the case where the correlations is everywhere positive. So in that case, even if there are oscillations like this, the previous result, the Gen's result, the Gen and Swansing and others, and Basler remains correct. But there is something even more interesting to it, because let's assume that we have a control parameter. Please go back. Yeah. Where is the mic? Yeah, thanks.
So in this, like this V of X, let's say the first one or the second one, so are you also assuming something, what happens at X goes to minus infinity is sufficiently confining or something like that?
What?
Yeah, this plot, for example.
This plot?
Yeah, if X is, let's say, goes to minus infinity, is it sufficiently confining or?
No, there is no difference between positive X and negative X. It's just...
No, what I'm saying is that you're looking from this bottom of the well to the climbing the mountain and going, right?
You're asking, okay.
Yeah, but I mean, unless this is sufficiently confining, it might even have a power law, this thing, right? Because it might just go far away to the left and never come back, or it take a very long time to come back.
Oh, I see. I understand the question. The question is, if the configuration, if the potential configuration is like this, why would particle climb here? I mean, if it can go the other way.
And then go all the other way. I mean, unless you say something
actually,
what when...
Okay. How should I answer this question? Well, there is no particle here right now. I mean, it's just computing the potential, the optimal configuration of delta V. So what you're saying essentially that if this is the result, why should I compute the escape time across this route and not across this one? I need to think about it, how to answer this question correctly. I don't want to guess. I need to think about it. Thank you for this question. Yes, of course. Of course, no, of course, I condition it to happen on this route, but the question is, you know, I'm thinking forwardly, you know, about the bottom, about the bottom line. Because at the bottom, when I make a statement at the end, I don't condition on anything. I just want to know, I just put a particle, I wait for it to come across the potential barrier, and then I change the realization of the potential, and I again put the particle, and I make averages, you know, if I do simulations, if I'm crazy enough to do simulations like this, you know, average both over the noise in a specific potential, and then average over the many potential realizations. What I get there, will it be describable? This is how I understand your question, and this I need to think it over. Okay, and again, actually I need to wrap it up. And so the presence of two different regimes, I mean, essentially there are two different solutions. There is a solution when L goes to, well, L is infinity, capital L, and there is a solution for a finite L, which appears in this case, when there are negative correlations in the system. And I can think about an imaginary, a Gedanken experiment with the medium, where I can control the correlation properties of the potential. And I think in the controlled experiments with colloidal particles in a potential landscape created by the laser, this is a possibility. You just change some parameter continuously, and you get from a regime where there are no negative correlations to a regime where there are negative correlations. So this is like a control parameter. And now you have two solutions. You have one solution which is better. I mean, the action is smaller in one regime, and then there is a switch between the solutions. So it's a classical first order phase transition picture, when at the transition the action is continuous, but the first derivative of it is discontinuous because you just go from one branch to the other. So it's like a dynamical phase transition when the control parameter is a parameter that controls the disorder. Okay, so my dream is that somebody would, try to see something like this in experiment with colloidal particles. Okay, so I have a brief extension to a non-smooth potential. Actually, there is only one process that is both Gaussian and Markovian, up to rescaling. This is essentially the Ornstein-Uhlenbeck process. And here we can use the optimal fluctuation method in its, classical version, because it's a Gaussian, it's a Markovian process, even without using the Gaussianity. And you can just solve it. So this is the correlation function, autocorrelation. And it is, of course, non-differentiable at x equals x prime, as we know. The first derivative jumps there. So this is the action. Now this is a sort of like classical mechanics, because you have, this potential part and this kinetic energy part. So we can solve it. This is the Euler-Lagrange equation. And you again have this kind of phase anti-phase, pulse anti-pulse optimal solution, which essentially is a particular case of the general formula. But here we get it without demanding any differentiability. So, and of course, in this case, this is a monotonic covariance, monotone decreasing covariance. So the correct solution is L going to infinity, and we can calculate the action, and the action is exactly what it should be according to the general formula. Okay, and now I didn't assume the smoothness. And just to the level of an advertisement, to other works, relatively recent works, where essentially the questions that we asked were quite different, but the technique was similar. You essentially abandon the Markovian property, the processes are non-Markovian, but you exploit the Gaussianity. Okay, so you use the Gaussianity to advance in the sort of optimal fluctuation analysis. And one system is somehow related, distantly related to what we had in the morning. But in this case, it's just a long time average in a system which describes a stationary Gaussian, but not ops processes. There is an extra E there at the end. Some stationary Gaussian process, and we can ask ourselves, what is the probability to see an unusual value of the long time average? So following the earlier paper of Nicholson and Touchette, we did these calculations 3 years ago to see whether the same phenomenon happens for non-Markovian processes, and indeed happens. And much more recently with Gleboshanin, we consider a fractional Brownian motion, which is now non-stationary. It's of course non-Markovian. It's not stationary anymore, but it is Gaussian. And we can ask ourselves all sorts of questions about large deviations of a fractional Brownian motion. what is the probability to have an unusual area under x of t if it is a bridge or if it is an excursion, okay? Or what is the first passage area distribution, area distribution under this fractional Brownian? A bunch of problems like these, like toy models like this, can be solved with a similar formalism. And in all of them, at the end of the day, you don't need to know the inverse kernel, which would be quite hard to find. It can be found, but it's not an easy problem to find it. We will post a paper with Gleb and Olivier Benichou in a few days, where we did find the inverse kernel for the fractional Brownian motions, but in simple problems. I need to talk about it. Actually, I doubt that. For the Mandelbrot Van Ness. For this one. For two-sided or one-sided? Oh, which means one for one-sided, yes. Okay. Mm-hmm. Yes. Right. Okay, and there is a closed form expression. We need to talk about it, because yeah, I remember these papers, but I want to make it sure. Let's talk about it. Okay, I think I should summarize. Yes, I have 2 minutes left. So, what are the main results of this work? So, as I said, negative correlations of disorder can exponentially strongly suppress the activated escape of particles. I mean, more precisely, to very strongly increase the average time of escape, the average over the realizations. And here is like a general take-home message. So if we want to model particle transport in disordered media at low temperature, this modeling may require a more detailed knowledge of the correlation properties than it was believed previously, because people usually assume that knowing the variance of this process, of this disorder, is sufficient to say something, essentially to say everything about the transport. I mean, we found a counterexample to this, at least. And this is a more general statement that optimal fluctuation method can be very useful for certain kinds of large deviations of processes which are non-Markovian, but if they are Gaussian. So the future work, we want to include the external field, a constant field, just a drift. And this is an ongoing work with my student. And frankly, I don't know how to solve the problem in the case when this integral diverges. So when we have the power law correlations of the potential, and this power law is sort of non-normalizable. I just don't know, because the standard technique based on the inverse kernel breaks down. And I'm not familiar with any technique. So if anybody heard something about it, I'll be happy to learn about it. And of course, higher dimensions would be a nice thing to do, because there are sort of definitely new qualitative properties there. Thank you very much.